everyone, welcome to CC 373, section 4. We're going to talk about heaps for this video. So the first thing is, what is heap, right? So there are two types of heaps. The first one is max heap, which is every node is larger than or equal to its children. The second thing is min heap. So every node is smaller than or equal to its children. So what it really means is, so I hope you have time to think about what this heap will be correspond to which one. So clearly this is a mean heap because you can tell that 2 and 3 are greater than 1, 4 and 7 is greater than 2, 6 and 5 are greater than 3, and 9 is greater than 4. So all these small subtrees of this heap comply to the invariance where every node is smaller or equal to its child. So every node is smaller than or equal to its children. So that's what it means, right? So and one thing to really note is in this example, you can see that 6 and 5 are not in order. It doesn't really need to be because heap all the ordering are relative to your parent. So you only care about if your max heap, you need to be your node value needs to be greater than your children, whereas it is a mean heap, then your children needs to be greater than the parent, right? So that's one thing to note, so that this, as long as 6 is greater than 3 and 5 is greater than 3, then it is a valid mean heap. That's just something to keep in mind, and that is same for the max heap as well. In order to truly understand what heap is, we will need to understand some key operations as well. So the first thing is remove mean or remove max. So basically it removes the root of the tree for mean or max heap. So you can kind of think about, like, high level, we're removing like over a root. So for example, this is 1, right? So if we call, because this is a mean heap, the very first, like, over a root, which can be like a root, will be 1. So we are just, when we call remove mean, we are going to remove 1. But when you think about logically, okay, if you remove 1, then what's going to happen, right? So we have to figure out what we want to replace with and ask another question. So let's say we replace with some arbitrary values, and is that in a correct spot now, or all the invariants still meet? And the answer is, we cannot guarantee that the values are in the correct spot now with the replace value, some kind of replace value we'll later talk about. So we do need to call a method called percolate up or percolate down in order to fix the invariance of the tree after hand. So for example, if you think about remove mean, we'll replace with some value, and then but we need to make sure that replace value needs to percolate down to a correct spot, right? So then and if you think, oh, you're adding a value which we will append at the end of the heap, then it needs to percolate up to a correct spot, right? So those two operations are critical for insert and removal call, so that it guarantees our invariance. Yeah, and these operations are as simply as swapping value with its parents, as if that's necessary. So here is some heap runtime. So insert is log of n. As you can kind of see that the height of this binary, this heap will be, because we're adding it onto a the most right side of the heap every time, so that the height will be maintained as a log of n. Because we are not having the worst case, if you remember from binary tree, not binary search tree, then we could have possibly have like not self-balancing tree, but if you have something like some random binary tree, then we could have some kind of really linked list like looking tree, then that is not guaranteed to be then the height could be worst case O of n, which O of h, which is h is a number of nodes. But here we are always guaranteed to have log of n heights, because we'll be always appending at the end of the right side of the empty, the most right empty side of the, I guess, parent node. Okay, so remove mean is same, so it's log of an operation, because remember that when we insert and when we remove, we need to call this percolate up and percolate down method, and that will take maximum of log of n time. So always remember that. So this is one example. So when we say insert 7, we are always going to append. This 7 was appended because this is the most open, like rightmost place, right? The child, because 9 and 12 are full because this is binary heap. So the 7 will be inserted as a child of 17. But we need to question, okay, is this a valid heap now? It is not, because we know that 7 is less than 17. So what we need to do is we need to do a percolate up. It doesn't show, but you'll percolate up and it'll be 7, 17. And we know that the 7, the swap value of 7 is greater than 3, so we'll stop there. Another operation is remove mean. So we previously had something like this, right? And then we call some remove mean on something. So now this is empty, currently empty. So what we should be is we're going to get the most right value because that's the safest item to remove. So let's say we just remove like this 2 or 5, things will be much more complicated, right? Then we'll need to modify the entire tree, entire heap. But if we just take the very rightmost value of the tree and at the very last level, and if we make it as our temporal over a root, then we can just simply percolate down and just get its right place. So make sure that you need to call percolate up and percolate down in according scenarios.